Okay, from class last time, this is the same information I went over in class, but I'm going to go over it quickly now so you have reference to it. Y equals x squared. If y equals x squared, then dy dx equals 2x. What does that mean? Well, dy dx is the instantaneous rate of change of y with respect to x. So 2x is the rate of change of y with respect to x. That means that a change in y is approximately equal to dy dx multiplied by the change in x. It's approximately equal because if you're finding a finite change in y, then the value of dy dx is actually going to change as x changes, and x is also changing, so that the value of dy dx is in general not static, and that's certainly the case for 2x. As x increases, so does dy dx. However, if you make if x changes by just a little, then dy dx is going to change by just a little. And in that case, we can say that delta y is approximately equal to dy dx multiplied by delta x. Approximately equal takes account of the fact that the dy dx is changing, and you're not going to get the exact change in y corresponding to the change in x. But if the change in x is reasonably small, then the change in y will be predicted with good accuracy. Now, for notational reasons that I'm not going to try to explain, dy is in differential format. We use dy and dx instead of delta y and delta x. So that dy, the approximate change in y, is equal to dy dx times dx, and that's for the same reason that we just went over. So that in this case, dy equals 2x dx. Now that applies to the function y equals x squared. It wouldn't apply to another function. Now to the question of what does this mean, how can we apply it, we take an example where x is the side of a square. And dx is the uncertainty in the length of that side. So y equals x squared is the area of the square. But if we have an uncertainty in the length of the side, then we don't know that y is exactly equal to x, and what we want to do is get a handle on how much y could vary given the variation in x. So dx is the uncertainty in the value of x, dy is going to be the uncertainty in the value of y, and we're going to say that dy equals dy dx multiplied by dx. Same thing we said over here. We're just applying this differential. So that if x is uncertain by an amount x, y is uncertain by an amount dy. And we have a picture here. We have a square of length x. Okay, from here to here is length x, and from here to here is length x. We have x plus dx being the length from here to here. We have two strips lying at distance dx on one side and the other of the side, the actual, or the side of a square of length x. Okay? And we have the same thing up here on this side, so that this side might be as much as x plus dx or as little as x minus dx. Now, if we, excuse me, let me pause for a second. If the side is in fact x, then the area is x squared. So we say the area of this square is close to x squared. It's approximately equal to x squared, but we have this fuzziness, this uncertainty in the lengths of the two sides. Now we can say for sure that a is less than or equal to x plus dx quantity squared, because we are assuming that we're certain that the variation is not bigger than dx. Now sometimes we have a little fuzziness with that idea too, but let's make it concrete by saying that for the moment. Okay, so a is less than or equal to x plus dx squared. We can square x plus dx, and we get this expression, x squared plus 2x dx plus dx squared. Observing that if dx is small compared to x, then dx squared is going to be very small compared to 2x dx. So we say that dx squared is pretty much going to be 0. So we're going to put a little arrow here and say that's going to be pretty close to 0. Leaving us with the conclusion that a is less than or equal to x squared plus 2x dx. Now I could make this plus a plus or minus. Well, I can't make it a minus because then you wouldn't have the less than or equal. So I could put a greater than or equal to x minus dx quantity squared on this side. And you should probably do that just for the exercise. So you have a three-way equality here, and I'm going to claim that the equality works out like this if you, again, use the idea that dx squared becomes negligible. So the inequality you would get here by setting a greater than or equal to x minus dx quantity squared leads to this inequality to the extent that dx squared is negligible. Now, if you have a fairly large uncertainty, dx squared might not be all that negligible, but compared to 2x dx, it will still be a rather small term. And you have to make judgments when you use these approximations. So in any case, if this is the case, the area is uncertain by plus or minus 2x dx. And when I wrote this, I didn't bother squaring my x's, so hopefully that didn't cause anybody any confusion in class, but we'll correct it for now. So the area is uncertain by plus or minus 2x dx. This is area plus 2x dx. This is area minus 2x dx, where the area is x squared. Capital A is the actual area, which lies somewhere between here and here. Now we talk about the proportional error in x. And that's just the error, dx, as a proportion of x. And you should understand that terminology, that this gives the dx as a proportion of x. If this is expressed as a percent, by multiplying this calculation by 100%, you have percent error. The proportional error in A is what? For this example, again, for the example of the square, the proportional error in A is 2x dx, which is the uncertainty in A. And I'm using the words error and uncertainty kind of interchangeably, and I should be a little more careful about that. They aren't quite exactly interchangeable, but we'll get into that distinction. Okay, the proportional error in saying area instead of error. The proportional error in A is the uncertainty in the area, which is 2x dx, divided by the area that we think is most likely, which is x squared. And when this is simplified, it's 2 dx over x, and that's double the uncertainty in x. Now you're given the rule that if x is squared, the uncertainty, the percent uncertainty in x in x squared is twice the percent uncertainty in x. Well, here's the reason why. Okay, this is the reason that rule is as it is.